Hello all, my name is Thierry Epasa and today we will talk about an exciting study case. How ETAP Arc Flash Calculator helped me detect significantly flawed study across several states in America. I am the Director of Electrical Engineering at an engineering firm called EEEengineering LLC. I am also the owner of the firm. I did create 2 newsletters on LinkedIn where I frequently discuss the American grid, relays, power study, and ETAP. Feel free to connect with me. On the agenda, we will focus on playing with ETAP Arc Flash Calculator and showing the incredible benefit of that tool. I picked one example, 2 bars, out of the 5,000 pages of report of the total combined studies. The 2 busts were just one of the many significant issues. All the studies were done across 15 states, completed, PE stamped, and the Arc Flash labels were already installed. What is an Arc Flash study? We have this safety incident called arc flash. When an arc flash occurs, there is a release of heat that could fatally burn the worker. An arc flash study examines the entire electrical facilities and determines the risk of an arc flash incident. A report is written and it provides steps to eliminate and/or mitigate the consequences. There are significant challenges in reviewing the accuracy of Arc Flash studies reports. 1. Reviewing reports without accessing the source file from the software. I usually see reports being reviewed and approved solely by reading PDF. How do we know we are not missing something significant by not opening and running the simulation? Challenge 2. Reports are lengthy and daunting. Some reports could be 1,000 pages. It could be daunting and unnerving to review long reports. We may be tempted to scroll over the report and not focus on the critical details that matter. 3. Arc Flash key output are nearly impossible to hand calculate. Unlike short circuit current, load flow voltages, and few other data that can be hand calculated, it is almost impossible to hand calculate the calories or Arc Flash boundaries. Challenge 4. Equipment owners are sometimes safety personnel that has limited electrical power knowledge. Many times, the owner and/or approver does not have the necessary background to ask the right questions and/or test to see if the study looks accurate. An Arc Flash calculator is a tool that helps you eliminate some or all those challenges. As the name indicates, ETAP Arc Flash Calculator calculates many critical outputs of an Arc Flash study without building a simulation, assuming you already know all the input. Hence, it is a great tool to check the accuracy of studies when you have a PDF and/or cannot open the source file. Moreover, it is also a fantastic tool to visualize how changes in input and parameters can affect the calories and Arc Flash boundary. This is ETAP Arc Flash Calculator. I am currently using the latest ETAP version at this time of the video recording, ETAP 22.0.2. The icon is located here. It is actually called a power and Arc Flash calculator. When you hover over the icon, it says powered calculator. It does not say Arc Flash. A little tricky. I think ETAP should update that. Both of those images are arc flash calculators. The difference is the view on the right area of each image. On the left image, the right area shows the result interface. On the right image, the same corresponding area shows the plot. Let's go through some keywords in the interface. First row, you can pick what you want to do: power flow, AC arc flash, DC arc flash, or arc fault. For this presentation, we will mainly stick with AC arc flash. Here are the input parameters. NOMV, line-to-line nominal voltage of the bus. Bus bolted fault current in kiloamps. This is not the arc fault but the bolted fault. Conductor gap, distance between phase-to-phase conductor in millimeters. Working distance in inches. Height, width, and depth of the equipment enclosure containing the particular bus. They are in inches. Electrode configuration, VCB. A cool thing in the image on the right shows the representation of VCB. If you change to ECB, the picture reflects the new configurations. Fault clearing time, the time it takes to remove the fault. The total time will be relay plus breaker if there is a relay. On the right side, there are the results. This lecture will focus on the two key outputs: incident energy and arc flash boundaries. For this example, a 480 volt with 31 kA bolted current, enclosures having those dimensions, equipment gap, and 0.5 seconds fault clearing time. We have 18.21 calories and 131.64 inches for arc flash boundary. Notice, you don't have to build a model to get those outputs. You don't need a simulation file. So cool. Moreover, getting those answers using a pen and paper is nearly impossible. I know I can hand calculate this. Now on the right image is the plot view instead of the result. The top graph shows the arc flash boundary with the shock boundary. LAB means limited approach boundary. RAB means restricted approach boundary. NFPA 70E define those terms. The bottom has two radio buttons. IE versus FCT is checked and shown here. It tells you how the number of calories will change if you change the time of the fault, and all the other data remain. For example, at 2 seconds we have right below 80 calories. Those images show additional views. On the left, the bottom view now has IE versus working distance. As the working distance increases, you can see how the IE decreases. The right shows at the top a contour. You can see the flame and the arc flash boundary. Let's see how I use this tool to detect massive flaws. A facility owner and engineering firm called me to do a cold eye review of their quality control practice to assess their power studies, short circuit, low flow, coordination, arc flash reports, and a few more. The goal was to use the learning of my feedback for their upcoming reports. I asked them to provide me with previous arc flash reports, and we can start from here. They did not use ETAP software. Below is a snapshot of the arc flash result tables. There were hundreds of rows. Look at those two rows. I slightly modified the name of the bus so that I could retain confidentiality. This is why this color is different than the rest. You may ask, what prompted me to pick those two buses in my code as review? There are vital data I use to screen reports. We will not discuss those criteria today as it is out of scope for this video. This table shows me everything I need to populate the data on ETAP Arc Flash Calculator and see if the result from their study will match the result on ETAP Arc Flash Calculator. Result means instant energy, and arc flash boundary. Let's do it. Voltage 480 volt, bus fault current 19.10 kA, trip time 2 seconds, equipment type panel, electrode configuration HCB, height 65, width 35, depth 35. Remember, those dimensions are in inches, not millimeters. Gap 267, this one is in millimeters. Working distance 18 inches. Now I will input the same data on ETAP Arc Flash calculator and compare the result. This is a critical time. Are we ready? 3, 2, 1, let's roll. 480, 19.10, 2 seconds, panel, HCB, 65, 35, 35, 267, 18. Done. Now I took a screenshot and compared both. Look at the result of the study. 44.9 cal. ETAP 232.02. I did the same process with the transformer 2 bus. This time we go faster since we already know the process. The result of the study, 45. ETAP 231.42. There was a silence in the room. Impossible. ETAP calculator must be wrong, or there's maybe something I am missing. Well, this is what I told the group. Check this out. I will now make some change to your simulation file, and I will change 4 data: height, width, depth, and gap. And I will rerun the study on your software. Everything else will remain the same. There are no changes in current, voltage, breaker time, working distance, enclosure configurations. 14 inch, 12 inch, 10 inch, 25 millimeter gap. I will run the study. New cal number 138.2. Now on ETAP, I input the same data, same numbers. Bingo. 138 calories. It now matches these times. Your simulation file matches with ETAP calculator within 99% accuracy. Another silence. I love those silences. The arc flash analysis on those buses was significantly incorrect. Unfortunately, there were more buses with the same issue. There was also more buses with different issues that we won't address in this video. On this issue, the report had a fine print note telling them they may have issues because of the dimension of the enclosures and the gap. Now, the dimension and enclosure and the gap were correct. It came from the manufacturer and the drawings matched. However, the software had the limitations. Those bus results then used the old method from 2002. It automatically switched. When you run 2018, it switched to 2002. The software had a fine print note telling them. Now notice here, ETAP has the same fine print notes. However, ETAP did not change their algorithm to the 2002 method. They did an extrapolation using still the 2018 EEE equation and method. And that's why this calculator gives you a much more reasonable result. Besides this issue with the 2002 method used instead of the 2018, even though they selected the 2018 method, ETAP Arc Flash calculator also helped me find additional problems. One of them was the option chosen in the Arc Flash study model. That also led to significantly incorrect results on some other bus. I also use this calculator to explain the concept of arc flash regarding parameters and input changes. What happens if I increase the gap? Look at the calories and the arc flash boundary changing. If all the data remain identical and I solely increase the gap, calories increase. If I decrease the gap, calories decrease. This really matters because when we replace equipment with a different manufacturer, we do not often even look at the gap. When your ABB breaker is replaced by an Eaton breakers, all the nameplate data may have matched, but hold on, your conductor gap changed. Hence, your arc flash label is no longer valid even though the nameplate remain nearly identical. I caught flaws like that in some facilities. Working distance is changing. Look at how the calories behave. What happens when we play with electrode configuration? Which one is the worst case? HCB gives us 34.5, VOA 8.11. One tricky part is the current change. Look, if I increase the current, calories increase. If I decrease, calories decrease. Pretty logical, right? But hold on, not so fast. The assumption is that the fault clearing time stays the same in both scenarios. If you have a fuse, for example, the time can increase when you decrease the current. This situation is shown here. For 14.12 kA, calories are 34.5, but lower current 12.18 kA, calories are higher, 38.52. In conclusion, I really want to focus on one statement. Everyone heard that statement, garbage in, garbage out. Meaning, if you get the wrong data, you get the wrong result. It is a true statement. However, not garbage in, not garbage out is not a true statement. You can get the correct data and still get the wrong result. This was the case in this study case. We cannot solely rely on the accuracy of input data to determine if an arc flash study is correct. Anyone with a software license can produce arc flash studies, but you must know how to go above superficial mistakes to detect significant flaws. ETAP Arc Flash tool is a great tool to detect those flaws. However, you must know how to use the tool and learn how to interpret the result. For this study course, I helped them redo all their labels, and 6 weeks later, I received a call for one of the executives asking me if I wanted to become the Chief Electrical Officer for a substantial amount of money. Make no mistake, I am not more intelligent than the engineer. I just have the right tools and knew how to use them correctly. Thank you for joining me. I'm Cherry Pasa and I approve this message. Any questions?